Hi, I'm Udi, the chief scientist at Tuki Networks. I want to tell you about how we perform cryptography in our Tuki links. And usually in the blockchain space, you have wallets, which contain secrets, private keys, and public information, which is everything that reaches the blockchain or stored on the blockchain, transactions, addresses, contracts. And the secret is usually a scalar number, so I'll use a lowercase letter, and I use a red color to represent that it's a secret. And public information, I'll use a green color, and you can always derive a public information from a secret by multiplying the secret with the generator of the elliptical curve G and generating a new point on the elliptical curve. And here I applied also a hash function to get an address for this private key. In Tuki, we have an intermediate level, which I'll use orange to represent it. It's also secrets, and it's also a scalar, so it's also lowercase letters. However, this secret is shared between a person who creates a link and anyone who receives that HTTP link. And so this is not a secret which is just held by one user in its wallet. The secret is held embedded inside an HTTP link. And the idea is that each link creator, for example, the contractor that creates a campaign, generates a link with a secret, and only a limited group of people, let's say all the people that are in his Telegram group, know about this link, and therefore they are the only people who know what the secret X1 is. And the idea is that each of these influencers, the seed of the link, will convert the link and will also convert a secret in it into a new secret, and then pass it on to other people, other influencers. So these people in the next step will have their own secret, X2, and they will not know what the previous secret was. However, the link will contain some kind of a signature that shows that the previous influencer knew about the previous secret. So overall, the link contains a chain of influencers, each one proving that he knew the previous secret. And finally, the link reaches a converter, and the converter sends the link to the contract, and the contract simply verifies the signatures one after the other and verifies the entire link. And we found that there are like two types of ways of adding secrets. One possibility is that each influencer inside the same group adds different secrets. So let's say the contractor placed the link in the Telegram group, and we had two different influencers. Each one of them took the same link and modified it in a different way, added a different secret, X to A and X to B. And in this case, a link, let's say the link going like here, will contain the contract information, the address of the campaign, and the address of the first influencer, a signature of the address of the first influencer made with the first secret, but also the private representation of the next secret in line. And that private and that public key of the next secret in line will also be included in the signature. And let's say there is another influencer here, influencer number 2. This influencer will do the same. Will put his address, will put the public part of his secret, X3, and will sign his address and the public part of X3 with the previous secret, with X2. And what happens is when let's say this second influencer wants to converse. So this influencer will send the entire link without the secret to the contract. The contract will read off the address of the converter A2 and the public key of his secret, will use EC recovery to recover the public part of X2 and will compare it to what's stored here. And then it will, if everything goes well, it will perform again the same process backwards. It will take the address and P2 and concatenate them and do a recovery to get the public part of X1. And the public part of X1 is the anchor of this entire, all of the links, and therefore it's already was stored in the contract by the contractor when he created the campaign. So the solidity code in the contract can verify that the entire link is valid, and therefore the conversion is valid. And also, at the same time, it keeps note that A1 was an influencer, and later on, the contract will give a bounty to A1 because he was involved in the conversion. Another option of doing the same thing is to use a predetermined secret at each one of the steps simply by using a hash function. In other words, the next secret will be a hash of the previous secret and so on, and which means that other influencers here will all have the same secret. And in this case, the next influencer in line will have to concatenate the address of the previous influencer in order to make sure that indeed we're talking about a single chain of conversions of influencers from the contractor all the way to the conversion. So this concatenation of the two addresses is needed. And here, however, when this link is sent to the contract, the solidity code needs to verify that indeed the recovery of this one is P2. So therefore, also in addition to P1, all the Ps, including P2 in this case, are pre-stored in the contract by the contractor, but this is possible because all the secrets are known in advance. And the only part about the secret is that, let's say, influencer number 2 will not be able to know what X1 was because they cannot walk back through the hash function. But the contractor knew, for example, knew all the secrets, and therefore the contractor was able to store all the public keys in advance in the contract. The only limitation here is that the contractor needs to decide in advance that there will be at most let's say 10 hops, 10 values stored in the contract. And that's the only limitation here. The only thing I didn't discuss up to now is like what happens if each influencer wants to add a parameter, let's say what percentage of bounty he wants. And that could be easily done by adding another value to the what is being signed in each step. And I also didn't cover the lengths. So we saw we had either two addresses and two addresses for the influencer address and its public of its secret, and then which is 20 and 20 bytes, and then a signature which is 65 bytes, and altogether 105 bytes per hop per influencer in the link. Or in the second option, we saved just the public, need to store the address of the public, of the secret, and therefore it's only 85 bytes, but still it's a lot. And therefore in our implementation, we use the IPFS to store this information, and in actual HTTP link itself, we just kept the signature of the IPFS. And another problem is that the identity of the influencer is not secured. In other words, it's nothing guarantees that A1 was actually involved in doing the extension of the link that we saw, or A2. And so if the link is on a campaign of dubious aspects, somebody may not want to be involved in that campaign, and somebody else can say that actually he was the person who is the influencer, the person who is being involved in promoting the campaign without that person's permission. On the flip side, the identity of that, even if you are the legitimate influencer, your identity is exposed, and in some cases that is not wanted. So therefore, we have a new version which uses aggregated Schnorr signatures. And here again, the link starts with just a secret as before, and nothing changes. And now, let's say the influencer wants to, the first influencer that receives this secret wants to convert. So this time, the influencer will use a Schnorr signature, which I'll recap here. And the idea of a Schnorr signature is that you can't actually send X1 directly to the contract because you want it to be a secret, like orange. And so therefore you mask it with another secret, which is K star here. And you add the hash of your address, and that's how you form a signature. And you also need to compute the public of this new mask secret, which we call R star, and also add it to the hash in order to avoid some forms of attack. And what happens in the contract when you S now is green, because you cannot really derive back either X or K star from it. And so S is green, is safe to send the contract, and the contract, when it receives it, multiply it by the elliptical curve generator, G. And if we just follow the multiplication, and we get here K star times G, which is exactly R star, we have the same hash, which can be computed inside the contract because R star is also sent to the contract with S star. And finally, we have X times G, which is actually P1, which, as in before, is stored in the contract. So it's available for the contract. So the contract simply needs to multiply S star by G and see if it's identical to R star plus the hash times P1, which is stored in the contract. And the operation of multiplying here and here a scalar by a point on the elliptical curve can be efficiently done using a trick that Vitalik found. And this is all this operation costs on the order of 40,000 gas units. And now the question is, what happens in general? In general, each secret in a link is a hash of the previous secret. We saw that before. And here we have also a sum of signatures that we'll soon describe, one for each of the influencers and that contributed to the link in each of the hops. And each influencer adds a public part of the mask used in his signature, S. And so the only thing that needs to be extended each time is one more point on the elliptical curve, which is only 32 bytes. So unlike the 105 and 85 bytes per hop that we saw before, now over here we have only 32 bytes per influencer, which is a significant contribution. And what's this per influencer signature is simply, again, a Schnorr signature, which contains a random mask, K, with its public part, R, and the hash of all the R's up to now, up to this influencer I. And we need to concatenate all of them in the same way we had to concatenate all the addresses before. And the conversion is very similar. Eventually, someone receives this link and wants to convert, so he sends the R's to the contract and also generates a new S star signature with a new mask K star, which is completely random, which has a public part, R star, and a hash of his address, the converter address, with the secret XN. And all this sum of previous signatures of all the previous influencers that contributed to conversion. And the contract performed this operation. It simply multiplies S stars by G. And then what you get here is K star times G, which is R star N. And the hash can be computed by the contract. and this is Pn, which, as I said before, is stored already in the contract by the contractor, by the person who created the contract. And now you have to perform the same sum for each of the intermediate signatures. Each one has its own RI that, as I said, was all of the Rs are sent by the converter, and the hash also can be computed, and all the Ps are pre-stored in the contract, all the PIs. So the contract can compute all that. It will, of course, cost more gas, but it's doable. And the validation is simply comparing that the left and right sides are equal. So what we saw here is that each of the Rs somehow secretly identifies each influencer. So the problem is that K that used to generate R cannot be just the secret with which each influencer identifies itself, because K is known to sibling, to other influencers that saw the same link that our influencer, let's say influencer 1, saw, and also saw the link that the first influencer generated. Because if you take the input to influencer 1 and the output and subtract them, you can extract K1. So K1 is orange. It's known to anyone who knows the same link that influencer 1 saw. So that's like the problem. But on the other hand, if we really manage to solve this, we don't need to add the address itself to the link. So we save 20 bytes of storing, and also we keep the anonymity of the influencer, and also nobody can forge his identity. And so we actually solve all our problems by just solving how to use K here. And the trick is to have K as a new independent Schnorr signature made of a new secret X bar and the new mask value K bar. And each one of them has his own public part. K bar has R bar and X bar has P bar. And the hash here is, of course, concatenation of all the public information, include the address of the influencer. And the idea is that now, whenever ever a conversion happened, the R1, for example, was stored by the contract to signify that whoever is influencer number 1, he contributed through R1 to the conversion. And all that the influencer needs to do is to prove that that's actually the signature, that K1 is actually the signature showing that he owns R1. And the way to do that is to send the public information, R bar and P bar, to the contract with, and what the contract does is it simply calculates this expression on the right side, because it receives R1 and R bar and P bar, and can compute the hash for influencer A1 and see whether it equals R1. Now, anyone else will not be able to forge, will not be able to pick a pair of 2 points on the elliptical curve, R bar and P bar, that will exactly match this equation that we want here for R bar. And the only person who can actually supply R bar and P bar is only influencer 1, because he was the only one who actually was the one who created this signature with K bar and X bar, which always remain secrets. That's why they're red here. Okay, so that's it. Thank you very much, and I hope to talk with you soon.